Hi, hi. So this time we want to talk about the relationships between problems. So we want to be able to talk about that one problem is somehow harder than another, or takes longer to solve. So let's do that. Okay, so when we thought about incomputability, we considered a sense in which some problems are harder than others. So you might remember, for example, the halts on three problem. So there it is. It asks, if I give you the index of a Turing machine, can you tell if it halts on input three? So we looked at that problem among many other similar ones, and we showed that if you could solve it, then you could solve the halting problem. So we denoted that with somehow a less than sign. K, the halting problem solution, is a less than or equal to sub t, t stood for Turing, s. So in some sense, S was somehow a bigger than or greater than or equal to problem. It somehow knowing S tells you at least as much as knowing the Turing machine. It's going to be knowing the halting problem. All right. In general, a set is Turing reduces to A. Turing reduces to A. B less than or equal to sub t A if there's a Turing machine that computes B from an A oracle. So that if you knew A, you could ask some questions of the A oracle. Is 7 an element of A? Is 9 an element of A? Is 14 an element of A? Okay, and then use those pieces of information, do some kind of if then else, and come out with yes or no, the original input is an element of B. So said another way, we can answer questions about membership in B by being given access to a routine that can answer questions about membership in A. If you give me the a routine that says element of A, and I can answer questions about whether something's an element of B. And this is a general thing that's true in all of mathematics. In mathematics, we use the phrase, whoops. In mathematics, we use the phrase reduces to. We say that B reduces to A if you could solve B anytime, darn it, anytime you can solve A. Sitting in a funny position. If you could solve B anytime you could solve A. I'm going to note that the phrase is a little backwards. Sometimes when you write something like B Turing reduces to A, sometimes people get the phrase reduces to backwards because somehow this makes it look like you're taking A and reducing it to make it down to a smaller size B. That's not right. That in fact B reduces to A is the terminology. That if you could solve A, then you could solve B. And the example that I gave there is that finding the maximum of a list of numbers reduces to the problem of sorting that list. So max is less than or equal to sorting. If you could sort, you could clearly find the max. Okay, and there's some sense in which this problem here, the problem on the bigger end of the greater than or equal to sign, is somehow at least as hard as the problem on the other end of the greater than or equal to sign. Well, we want to extend that in this chapter. We want to extend that to the problems that we're studying. Specifically in this chapter, of course, the way we're interested in classifying problems is how hard are they? We can solve them, typically, but we want to know, can we solve them quickly? So let's think about that in the context of a couple of concrete problems, because I'm a concrete problem thinker. So I have two different problems. Vertex-to-vertex path problem, sometimes called ST-con or just plain path. Given a graph and two vertices, decides if there's a path between them. And then we have the shortest path problem. You're given a weighted graph and two vertices. Find the shortest path between them. And a person thinks, well, if you could find the shortest path, then you could for sure find the vertex-to-vertex path. If you could find the shortest path, you could for sure find if there is a path. So in some sense, shortest path is somehow a more complicated problem, or greater than or equal to complicated problem, than vertex-to-vertex path. More in the sort of context of this chapter, if you could solve shortest path quickly, then you could solve the vertex-to-vertex path problem quickly. Is what we're after. So as a run-up to the definition, just trying to think about all the parts of the definition that are to come. As a run-up to the definition, we first state them as language decision problems. So here I have the language decision problem for vertex to vertex path here. And here's the language decision problem for shortest path. And you'll remember that when we try to do an optimization problem as a language decision problem, we put in this parameter b. Okay, so if you can solve, we're claiming if you can solve the shortest path problem, then you can for sure find the is there a path problem. A person might notice that there's a bit of a type issue, is that in this top line here, G is unweighted graph, and in the bottom line here, G hat is a weighted graph. But we can patch that up by taking the unweighted graph, we shift it over to be a graph where every edge has weight 1. And so we're not gonna worry too much about that type problem. So here's the idea, and the idea is straightforward, is that I've written an algorithm here that tells you how to convert a question of is there a path at all into a question of is there a shortest path. So that if you could solve the shortest path problem, then you can solve the is there a path at all problem. Very straightforward. You read in the question about whether there's a path at all, and that's written as a triple because that's what it said on the prior slide. I'm going to do that type issue of converting the graph G to a weighted graph G hat, just to straighten things out. And then I want to find the shortest path on G hat between V0 and V1 with the bound equal to the size of G, so that I've got a reasonable bound, and I'm just trying to do it, not an unbounded problem, just trying to do it in the sort of length of the number of nodes. Okay, now if you're able to answer this box here, this is the oracle here. If you're able to answer that box there, then you can answer whether a path exists or not, and you can either print 1, meaning yes, there is such a path, the answer to the originally posed question is yes, or no, there is no such path, the answer to the originally posed question is no. Observe that this is fast. That if shortest path oracle is fast, then the rest of the flowchart is also fast. Okay, so we can leverage that oracle to give an algorithm that solves vertex to vertex path. All right, so ready for the definition. So here we go with the definition. So you take L0 and L1 to be languages, and we're interested, of course, in language decision problems. Then L1 is polytime reducible to L0, carp reducible, polynomial time mapping reducible, polynomial time many one reducible. You hear all those phrases. I'm going to use the phrase polytime reducible. And you write it less than or equal to, kind of like less than or equal to with the sub t, except it's less than or equal to with the sub p for polytime. You do sometimes see this, a sub m for many one reducible and a super p for polytime, but I'm going to use this. If there's a reduction or transformation function carrying input strings to output strings, that is polytime computable, and so that sigma is in L1 if and only if f of sigma is in L0. So you can answer questions about L1 by posing those questions to an L0 oracle. F translates the questions you asked in L1 over into somehow questions that are in L0. And in terms of the previous slide, for example, we had to convert the graph to be every edge has weight 1, this kind of stuff. We had to give a sensible bound, this kind of stuff. So what F does here is somehow expresses the problem, it expresses the L1 problem in L0 terms. So in some sense, what's happening here is that we are rewriting, we are rephrasing the L1 question into an L0 question and then just asking the L0 oracle. F is required, the rephrasing is required to happen in polytime because we're in chapter 5, so this is a polytime. It helps to have some mental idea of what's going on, so I drew a picture of all the problems here. This is all the problems. So all languages. Whoops, I spelled languages wrong. Come on, where's the eraser? There we go. All languages. And I didn't want to draw, there are uncountably many of them. I didn't want to draw all the languages, but I drew a bunch of dots to indicate that there are all those languages scattered throughout the diagram. And down there is P. This is all the computable languages are in here. And what you get with this less than or equal to sign is you get a connection between languages. Here we have two languages, and the one on the left is less than or equal to the one on the right. In some sense, what we have is that the one on the right is somehow a bigger problem, is a more knowledgeable problem, is it's got more information in it. Taking back to the description in the previous slide, where if you could solve sorting, then you could solve find the max. So over here, this is like sorting, this is like find the max. So the easy problems, the ones with a fast algorithm, are on the bottom. That's the way we always draw it. Problems are shown connected if there's a polytime reduction from one to the other. If you can take a problem like this one right here and rephrase it, oops, I pointed to one that doesn't have an upward. There we go. If you can take a problem like this one here and rephrase it as a problem like this one here, then you draw a line from the one to the other. Okay. I specifically highlighted the connections inside of P. Okay, so I want to do one example, and I want to try to go into what I mean by rephrasing. And then we'll stop, and then, you know, a person can try some homework problems, and then we'll come back with some more examples. Okay, so I'm reminding you how it goes. The clique problem is the decision problem for the language. You take a graph G and a bound B. Excuse me, well, I'll just take a parameter B. And so G has a clique with B vertices, and you'll remember what a clique is. A clique is where all of the vertices are mutually interconnected. So like so, like so, like so, and like so. You may have a larger graph outside here, and there's some additional connections in the graph, but a clique is when everybody in the four tuple, that would be a four clique, everybody in the four tuple is mutually connected. We're going to show that satisfiability reduces to clique. So intuitively, clique is as least as hard as satisfiability. Okay, so I've tried to phrase this in terms of you think of satisfiability as being rephrasable as a clique problem. And the F function, the reduction function, the translation function, does that rephrasing. So I want to do an example where, you know, where I explain that, where I talk about what's happening here. All right, so here is a specific Boolean expression. I'm going to ask whether it's satisfiable, but I want to study the Boolean expression for a second. Of course, the way I've written the Boolean expression, I have the ands, A and D, between the clauses, and the ors inside the clauses. Inside the clauses, inside the clauses, and inside the clauses. Think about the ands first, the A and Ds. Because of the nature of A and D, because of the nature of and, the only way you get the entire expression to be satisfied is if every single clause is satisfied, every single one. So it's a for all. Okay, what about inside of a clause? How do you get inside of a clause to be satisfied? Well, you got to have that any one, maybe two or three, but at least one of these are called literals here, the x0, the not x1, and the x2, those are literals. So any one of the literals is comes out true, then you're good. Any one of these literals comes out true, then you're good. Any one of these literals comes out true, then you're good. So when I ask, here's an expression capital E, can you satisfy it? What I'm asking you for is I've given you a bucket, sort of 3 buckets, 1 bucket, 2 bucket, 3 buckets. And I've said, is there a way to reach in and pull out from the first bucket, one of the literals, pull out from the second bucket, one of the literals, and pull out from the third bucket, one of the literals, and make those true, and then you're good. So a person thinks, okay, let's see, I'll pull out the bucket, from the first bucket, I'll pull out x0. I'll pull out from the first bucket x0. And from the second bucket, I'll pull out, how about x2? And from the third bucket, I'll pull out not x1. I crossed off the 1 in the not x1. I'll pull out the not x1. And so, yeah, all right, that's good. So that assignment, x0 is assigned the value true, x2 is assigned the value true, x1 is assigned the value false. That assignment makes the expression as a whole true. The only thing you could do wrong, the only mistake you could make in one of these assignments is you cannot do this. You cannot pull x naught here and not x naught from here. Because you can't have both x naught and not x naught be assigned the value true. That's a no-go. So one way to think of satisfiability is you've got these buckets and you're asking the question, is there a way to pull one thing from each bucket, at least one, but anyway, one will do. Is there a way to pull one thing from each bucket in such a way that never are you pulling it's called an atom and its negation from two different buckets? So it's really a combinatorial problem. Is there a way to pull from each bucket, 1, 2, 3 buckets, in such a way that never are you pulling an atom, never are you pulling an atom in its negation? Okay. So down here, we can think of satisfiability as a combinatorial problem. The closets are the bucket. We're required to select one thing from each bucket, subject to the constraint that the things we select have to be pairwise compatible. Never can you pick x naught and not x naught. Never can you pick x2 and not x2. And in this particular problem, of course, it was perfectly possible, very easy in fact. But you can imagine a problem with thousands of clauses, and it turns out if you pick the x1 in the first clause, then you're forced to pick sort of thing. So we have a notion here of compatible. There's a relation between literals of compatible. So I get a graph. I'm going to have to flip back to the prior page, but flipping back isn't the crime of the century. In the first clause, in the 0th clause, there was an x naught, a not x1, and an x2. In the other clause here, there was a not x naught, an x2, and an x3. And finally, in the final clause, there was a not x1 and a not x2. And I won't keep flipping back, but just once. You see them there, the not x1 and the not x2 in the final clause, just as a reminder. I made a connection here. I don't know how many connections, 1, 2, 3, 4, 5, there's a lot of edges. I made a connection between any two nodes when those two are compatible. So just as an example, I'm allowed to pick from clause 0 x2 and also from clause 1 not x3. Those two are compatible. I'm allowed to pick from clause 0 x naught and from clause 1 not x3. That would be okay. I'm not allowed to pick from clause 0 x naught and from clause 1 not x naught. I'm not allowed to pick that. And the other thing I'm not allowed to pick, or I want to pick one thing from each clause, so I have not connected things that are together in a clause. Okay? So I want to find 3 mutually compatible nodes here. So yeah, I want to find a clique. I want to find a 3 clique. Make 3 mutually compatible literals from the 3 buckets. So I have given a way to describe, to rephrase satisfiability as a clique problem. You make a graph of a certain kind, and then you say to yourself, I can solve satisfiability if I settle the clique question on that graph. A choice of 3 mutually compatible vertices makes the expression from the prior slide, I won't keep flipping back because it's annoying, makes the expression from the prior slide be true. So that is, the 3-clause expression E is satisfiable if and only if G sub E, the graph that's right above here, has a 3 clique. Now, ordinarily, when you see this written up, it isn't written at great length. People tend to be a little bit more parsimonious. So more formally, the reduction F that takes you from the expression E to the graph G sub E, the reduction function F inputs a propositional logic expression E and outputs a pair, G sub E comma B, where B is B is in this problem was 3, is the parameter. And obviously then E is satisfiable if and only if F of E has a 3 clique. So if and only if the graph G sub E has a 3 clique. And obviously, this function can be computed in polynomial time. I mean, polynomial time includes, like, big O n to the 100. I mean, come on. I can draw this graph in big O n to the 100. Come on. Okay, so what I'm trying to characterize is that when you go back to this definition, that one way to think of the function is that a function translates problems from the language of L1 into the language of L0. So we can see one problem as a kind of, maybe a special case of, but anyway, a kind of other problem. So we can see L1 problems, in the case of my example, satisfiability questions, as a kind of clique question. So if somebody came along and said, I've solved clique, you go to a talk and you're sitting there and the person writes on the board, the clique problem is satisfiable in polytime, you'd say, aha, I know how to solve satisfiability in polytime. That would be great. No, not happened, but it would be great. Okay. All right, so very good. So, so I urge you to try a couple of the homework problems, so that you start to develop some feel for it, and then the next video is going to do a couple more. Okay, very good. See you then.